Welcome back. This is the third video in Chemical Reactions unit. In this video, I want to introduce you to the types of chemical reactions. This won't be completely new. And then I want to kind of show you the patterns that these reactions follow, because our objective at the end of this is going to be able to look at reactions and classify them as one of the 5 types. For now, we're looking at the whole reaction, but in a few days, I want you to get to the point where you can just look at the reactants only and then classify the type of reactions. So that's where we're going with this, but for right now, let's focus on the whole thing. So first of all, there are 5 types of chemical reactions that we're going to learn about this year. The first is a synthesis reaction. The word synthesis means to make, and that's pretty much what a synthesis does. Number 2, decomposition. These reactions are the exact opposite of synthesis. You break something apart into its pieces. Then you have single replacement reactions and double replacement reactions. We've already seen double replacement reactions in the solubility unit. We did a little lab with precipitates there. So I hope you know the idea behind double replacements, the double partner swap. If you understand that and you learned that in the previous unit, then single replacement should be very easy. It's the same idea, except that you only have one partner swapping instead of both. We'll see some examples. And then finally, we're going to be looking at combustion reactions. Now, combustion reactions are a subset of synthesis reactions. They're brought out on their own for a couple different reasons. One is there's synthesis, but we don't have just one product, we actually have 2 products. And then another reason is that they're also better explained by the redox concept, which we're not really going to get into. But combustion reactions, things burning, are common enough that it's usually felt that students need to be introduced to combustion. The combustion reactions that we're going to look at are just hydrocarbon combustions. These are compounds made up of only carbon and only hydrogen. So we're doing a real specific subset of combustion. I'll talk more about it when we get there, but I have the potential to open up a Pandora's box there if I'm not careful. So our objective is to be able to identify the type of reaction and then eventually predict the products if we have only the reactants. So let's start with synthesis. If you look at the flow chart that you should have gotten in class, you can see that there are lots of different types of synthesis. Synthesis just means to make. So when we put 2 things together, those reactants can be both elements, they can be an element plus a compound, or they can be both compounds. So the easiest synthesis is reactant plus reactant to make one product. And again, those reactants could be elements or compounds. If they're both elements, so element A plus element B, they just smash together to make element AB. That's a very simple synthesis. All you have to do is worry about is thinking about charges as you put those 2 things together to make sure the charge is balanced, like we've been doing with ionic forever. Here's an example of that. If I put hydrogen and oxygen together, they make water. So I didn't just smash it together to make H2O2. I thought about hydrogen's charge plus 1, oxygen's charge minus 2, and made the combination that way. And then eventually I balanced it to keep in the number of atoms to obey the law of conservation of mass. So here's another example. Carbon plus oxygen makes CO2. Those did just smash together, but that's because here carbon is plus 4. So this is kind of the goofy idea behind synthesis. You take one thing, add another to it, and you get something that combines to make something bigger. Here's a better chemistry example of a synthesis. In this flask here we have, in the beaker we have potassium. It's kind of hard to see, but it's a little piece of silvery metal, and it's in the solid state. And then in the flask here, we have some chlorine gas. Notice the yellowish color to it. When these are mixed together, we'll see some clues of a chemical reaction, including a light given off. If you could put your hands on it, you would notice some heat being generated. And in the end, we can see a color change. So lots of clues of a chemical reaction. What we've made here is a combination of potassium and chlorine called potassium chloride. And you can see in the picture here it's a solid, and the lattice structure has changed. So that's a synthesis reaction. We're going to skip the practice for now because we'll have plenty of time to practice. Decomposition reactions, I mentioned, are the opposite. So we're going to take a reactant and break it up into its pieces, which will be the products. If I have compound AB, I could just break it up into element A and element B. For example, if I take that water, run some electricity through it, for example, I can break it into hydrogen and oxygen. If I have mercury 2 oxide, I can heat it, and I can get mercury metal by itself and then oxygen by itself. So this is kind of the goofy idea behind decomposition. You have an egg, it hatches, so at the end you have an empty eggshell, and then, in this case, a turtle. Kind of dumb. Here's a chemistry example. This is the one we just saw, actually. Here we have an orange compound. It's ionic, it's powdery, called mercury 2 oxide. We're going to heat it up. Notice the triangle. And when this is over, we can see color changes. We have this little purple intermediate, and we have some, looks like some steam. And then a definite color change here is we have liquid mercury, the silvery color. And then we would have seen some bubbles maybe as oxygen gas was driven off. Now, we decompose some compounds that, especially those that are called ternary compounds, we don't go all the way to elements. So when we decompose, we may have, I don't know what you want to call it, some preliminary products that we can get in an easier stage. So for example, here we have calcium carbonate. There's 3 elements here. So we don't necessarily heat it to the point where we get calcium by itself, carbon by itself, oxygen. Instead, if we heat it a little bit, this compound will break up and to give me 2 compounds, CO2 and calcium oxide, which is called lime. Chlorates do something similar, but in this case, they break up to give me 1 compound and an element. And so there are some rules for this, but it's a lot of exceptions, a lot of ifs, ands, and buts. The flowchart will help us out with this as we get into predicting products. But what I want to show you was that in decomposition, you can go all the way down to elements, or you can go, in this case here with calcium carbonate, to 2 compounds, or with aluminum chlorate, an element in a compound. So let's skip the practice again, and let's get to single replacement. So this occurs when one element replaces another in a compound. And I scrolled all the way to the bottom because I wanted to show you this picture here. This is the traditional chemistry explanation of having people at a dance. So here you see this couple dancing, a boy and a girl, very traditional. And then here you see this studly guy here. By the way, let's go ahead and label the couple here. The guy is a positive and the girl is a negative, so they're ions. And so we have here this studly cation walking in, and he wants to dance with the girl. Well, if he wants to make this happen, he has to somehow replace the guy who's already dancing with the girl. Now, it's a fight, just like you would see in nature. You don't just walk in and do it. You have to be able to overcome the bond that's already there. In other words, the bond between this guy and this girl. So as you can see, this guy is very studly, bigger, more attractive, more active, and so he easily breaks the bond, sends the poor guy packing, and he dances with the anion in this case. So that's the premise behind single replacement. Someone always gets kicked out and left alone. Now, I do not want you to think this always happens to be with metals, because nonmetals can also do this. In other words, I could have the same situation down here, but instead of a studly guy, I could have a studly girl come in. And she would kick out this girl and try to dance with the guy who's already there. So metals replace metals, nonmetals replace nonmetals. And that's the idea behind single replacement. Here's a chemistry example of single replacement. We have lithium plus water. So you can see here a piece of lithium, kind of a dull gray, and then into some water. We can see our clues of a chemical reaction, some steam, so gas, some bubbles, color change, and at the end we go back to having a clear solution. We've made lithium hydroxide and hydrogen gas. So if we look at what happened, H and O were dancing. H was the guy, O was the girl. Lithium comes in. Lithium is also a positive ion, or wants to be a positive ion, so it has to kick out the hydrogen. And that is exactly what happens. Our clues prove it. So lithium started dancing with the oxygen. It's a little bit more complicated here. It's not a great example. And then kicked the hydrogen out by itself. We'll talk more about what's going on. This is not, I could have hopefully found a better example. All right, here's a good one. Zinc metal reacts with hydrochloric acid. So again, H and Cl are dancing. H is positive. Zinc is a metal. It could also be positive. So it wants to kick out H. It does. So zinc and chlorine start dancing. Notice that I had to adjust the subscripts to balance the charges. It didn't just become ZnCl. It had to balance the charges, and that left hydrogen by itself, and hydrogen's diatomic. Here's another example, but in this one, fluorine is the element by itself. Fluorine wants to come in and break up this dance partner, NaCl, but since fluorine's a nonmetal, it needs to replace the chlorine here. It does that, so sodium begins dancing with the fluorine. Notice it goes back to just F because balancing the charges again, and that leaves Cl by itself. Let's just see if we have this. Think about what these partners would be. If you said Al would kick out copper to make aluminum nitrate, you've got this concept going, and copper would be by itself. So aluminum nitrate plus copper metal. And then finally, double replacement reactions, same idea, except we've got two partners, and we're just going to do a complete swap of each other. We've seen this reaction twice already with acids and bases and precipitates. So AB plus CD, notice that in each of these cases, A would be a cation, C would be a cation. They're not going to dance together. So A is going to swap partners, kick B out, and start dancing with D. And then we see the same thing with C, and wants to dance with B. That picture is totally ridiculous. All right, moving on. It's kind of like the FOIL method in algebra. So you can think about it, the first ion, in this case Ag, typically goes with the last one, so in this case chloride, and that means the middle two go together. So that's one thing you can use from your past to help you keep this straight. But again, we've already done that, and I don't want to spend a lot of time letting you sit through a video watching us do something we've already done. So that's double replacement. Now combustion reactions, these are really kind of easy. As I mentioned before, we're only going to burn a hydrocarbon fuel. So this is going to be a carbon-hydrogen compound. To burn something, we've learned years and years ago that we have to have oxygen, you have to have the fuel, and then you have to supply an ignition. Okay, so this isn't like a hot plate. We just got to get this thing going with a spark to overcome the activation energy. And once that happens, the general combustion reaction is you take your hydrocarbon fuel, react it with oxygen, and you get CO2 and water. There will always be CO2 and water, because what's happening in combustion is I'm taking the carbon and I'm oxidizing it to the most positive charge that carbon could potentially have, which is +4, and that's why it's CO2. And then I'm taking hydrogen and oxidizing it to the highest possible positive charge it could have, which is +1, and that's why it's H2O. That's all combustion ever does, is take whatever element you're burning and sends it to the most positive charge you could make that element be, and then you combine it with oxygen. So you could burn phosphorus, sulfur, and we'll do some examples of that in future practice, but that's a little bit beyond the norm. But that's what a combustion reaction is. And here you can see an example. Here we have pentane plus oxygen makes CO2 and water. We need to balance that. Here we have decane, 10 carbons plus oxygen. What would we make? That's right, CO2 and water. Well, this video has gotten obnoxiously long, so let's go really quickly through the practice. And I'm going to change these directions just a little bit. I'm going to write combination. We called it synthesis. And so we're going to either write S for synthesis, D for decomp, SR for single replacement, DR for double replacement, or C for combustion. So that's what we're going to do in the blanks. So looking at number 1, I see ionic compound, and I have 2 ionic compounds. It looks like lead has just swapped partners, so that is double replacement. Number 2, I'm looking at this one. I see only one product, so that's a good clue. If there's only one product, that's most likely a synthesis. And what I can see here is that I just kind of combine everything together. That's a synthesis reaction. Number 3, real quickly I notice a new partnership from swapping, so this goes back as another double replacement. Number 4 is just putting 2 things together. I know they're not balanced, but that's fine. This is a synthesis reaction. Number 5, it seems like we only have 1 or 2 types so far. Another double replacement. Number 6 is a little different. 2 products, but only have 1 reactant. That is an excellent clue that you are dealing with a decomposition reaction. Notice how that reactant breaks up into pieces. Number 7, I have 2 reactants, 2 products, but that's a lone element, and that's a lone element. And so I can tell that we have swapped partners, but only one thing changed. That's a single replacement. Number 8 is a little bit more difficult. I can see calcium and phosphate are new partners. It looks a little weird because the potential partnership between H and CO3 doesn't look like you would expect. We're going to learn more about this as we predict products. The H2CO3 that was formed will break up, but this is actually still a double replacement. Number 9, I hope you can recognize very quickly from the plus O2 and then the CO2 in water, that is combustion. Number 10, I can see here 2 compounds, a new partnership, double replacement. Number 11, same thing, new partners. Number 12, CO2 in water, combustion. Number 13, 2 elements by themselves make 1 thing. It looks like a synthesis. Could that be combustion? The answer is yes. Remember I told you combustion reactions are a synthesis type of synthesis reaction. This time we'd be combusting iron, which is just oxidizing iron to its highest charge, which is +3. And that's exactly what you see here. So either one would be okay for that one. Number 14, I'm sending magnesium away from phosphorus, from the phosphate, so that is a single replacement. It's being replaced by hydrogen. I hope you're seeing the pattern here. You're starting to work some of this stuff out. Number 15 is another one of those more complicated double replacements because we're making something that breaks back up. 16 is synthesis. 17 is another double replacement. 18 is another single replacement. And 19 is combustion. And then 20 is decomp. So you gotta have your own practice now to work. I hope you understand this, but if not, bring it to me and let's do some of these together and I can make sure you start looking for the patterns that you need to find.